So now we're going to do that same problem again, but with the divergence theorem. So remember, we still have this hemisphere, and that hemisphere still casts a region down into the xy plane, like that. So this object right here is x squared plus y squared plus z squared equals 25. Okay, now to use the divergence theorem, we're going to need f, the vector field, and we're going to need the divergence of f. So let's find those things. So f was x squared, y squared, z squared. And I need the divergence of f, which is the dot product of the del operator and f, which it would be the partial with respect to x, the partial with respect to y, the partial with respect to z of x squared, y squared, z squared. We don't have to do what we did with the other method. The other method required us to do all this work with z and like finding another function for z and then substituting and all of that stuff. We don't have to do that with the divergence theorem. We can just avoid all of it. So you just take the derivative with respect to x, which is 2x, the derivative with respect to y, which is 2y. Oh, this is a dot product. It's not a vector, so we're adding these. So 2x plus 2y plus 2z. Done. There's the divergence of f. Okay, so the divergence theorem says that the flux for this surface will be equal to the triple integral over the whole solid of the divergence of f dv. Okay, so let's think about this for a second. If I want to set up v dv, I want to set up this whole solid, right? This isn't going to be a two-dimensional thing like it was in the previous section, or the previous example, previous method, where we were making everything into a double integral, so we had to kind of get everything down into the region. So we're doing a triple integral here of a sphere. Now that means that we have two options available to us. We have spherical coordinates and cylindrical coordinates. And either one of them would work. It's just kind of whichever way we want to go. But considering our divergence has x, y, and z in it, and we know how those are going to easily translate into cylindrical coordinates, I would argue let's do cylindrical coordinates because they're easier. So let me make a note. Right, cylindrical coordinates are a three-dimensional version of a polar coordinates. Right, there's two ways to three-dimensionalize polar coordinates: cylindrical and spherical. You could use either one, but I'm going to use cylindrical. Okay, so if I'm going to go cylindrical, let's think. X would be 2r cosine theta plus 2r sine theta plus 2z. I'm going to let z be my third variable, right, because it has the lift, right? It's above the xy plane. And then we multiply that by r dz dr d theta. Okay, so actually, let me do these in different colors so we can see how they'll work. All right, so dz dr and then d theta. All right, d theta is easy because we know we're doing the entire sphere or hemisphere. So we know we're going from 0 to 2 pi. That's no problem. R, well, if we look at the region, right, that this shadow casts onto the xy plane. So this is the surface, and then this is the region. Well, again, we know that's a circle of radius 5. So that means R is going from 0 to 5. All right, now what about Z? Well, remember, Z is going to stack in columns from the bottom region up till where it hits that surface. So we're going from Z equals 0 down here to, well, let's see. If we solve this for Z, it'd be R squared plus Z squared equals 25. So Z squared equals 25 minus R squared. So Z is equal to the square root of 25 minus R squared. Technically it's plus or minus, but we only want the top hemisphere, so we're going to use the positive. So 0 to the square root of 25 minus r squared, like that. Now this is actually an easier integral to do than the previous one. For starters, these terms don't even have z's in them, so it's going to be no problem at all to integrate with respect to z, right? So let's write that out. This is the integral from, I can't make the 0 to 2 pi go away because I still have theta inside here, so it can't just disappear. And then I have the integral from 0 to 5 for r. But inside here, this whole thing is going to get multiplied by z. And as a matter of fact, it's going to get multiplied by an r as well. So it's really 2r squared cosine theta plus 2r squared sine theta. Those two pieces have no z in them, times z plus z squared. And we're going to take that from z equals 0 to z equals the square root of 25 minus r squared. And then we're going to have dr and d theta. So I did two steps there at once. I distributed my r to these two. Oh, and I forgot to distribute my r to there. R should go there, so it should be rz squared. Sorry, rz squared. Of course, I don't have enough space, so I have to write it this way. Rz squared. There we go. Okay, so I took these two and multiplied them by r. This one multiplied by r as well. And then these ones don't have a z in them, so I just multiplied them collectively times z. This one has a z, so I raise the power, right, and divide by the new power. All right, so everywhere there's a z is now going to become a 25, square root of 25 minus r squared. Okay, so this is the double integral from 0 to 2 pi still, and 0 to 5 still. And then it's going to be 2r squared cosine theta plus 2r squared sine theta, all times the square root of 25 minus r squared, plus r times, well, when you take a square root and you square it, it just becomes the thing, dr d theta. All right, so now, let's see here. You might think, oh, we could go to maple now. We could. Cosine theta and sine theta are the only thetas out here, and they're pretty easy. So let's do ourselves a favor, and let's change the order of integration. Right? There's nothing stopping us, because these are just numbers. It'd be hard if one of these was a function, but since they're numbers, we can actually just rearrange them and say, hey, I'll do the r later. I'll do the 0 to 2 pi right now. I'm going to do that first. So this would be 2r squared times the square root of 25 minus r squared cosine theta plus 2r squared square root of 25 minus r squared sine theta. And then this is plus 25r minus r cubed. This whole thing, and we'll do theta first and then r. Okay, so the integral of cosine is sine. The integral of sine is negative cosine. And if you'll notice, they're both multiplied by the same thing. So I'm going to be cute and do some algebra again. I'm going to kind of combine some like terms. So when I integrate this, this guy will get me sine. So, but notice how they both have the same component in front. So I'm just going to write that 2r squared square root of 25 minus r squared times the integral of cosine is sine. The integral of sine is negative cosine. I'm going to take that from theta equals 0 to theta equals 2 pi. And then plus 25r minus r cubed all times theta. Right? Because we have to integrate those with respect to theta. They don't have a theta in them. So they're going to also go from, well, I guess I should put theta equals 0 to theta equals 2 pi over here. I can erase it right here. because I have it at the end. Okay. And then we still haven't done the r, so I'm going to leave the dr right there to finish off my integral. Okay, so the sine of 2 pi is 0, right? So this is the integral from 0 to 5, 2r squared, square root of 25 minus r squared, times 0 take away 1, because the cosine of 2 pi is 1. So just to be clear, I want to put 2 pi in here twice. So sine of 2 pi is 0 minus cosine of 2 pi. And then I want to subtract sine of 0, which is 0, minus cosine of 0, which is 1. So if you notice what's happening, this whole thing, right, so let me just write this. This is sine of 2 pi, cosine of 2 pi, sine of 0, cosine of 0. But 0 take away 1, minus a minus 1 is plus 1. This whole thing is 0, so this whole thing is 0. That whole term is gone. And you're left with 25r minus r cubed times 2 pi take away 0. In other words, 2 pi. So this whole integral has reduced down to 2 pi times, right, because this whole piece is gone. So it's 2 pi times the integral from 0 to 5 of 25r minus r cubed, which of course is 2 pi times, let's see, 25 over 2r squared minus 1/4 r to the 4th. And we're going to take that from 0 to 5. And sure enough, right, it's going to become 625 over pi over, here, let me show you. It's 2 pi times 625 over 4, which is 625 pi over 2. By using the divergence theorem, we actually ended up with integrals that were, a lot simpler than the one that was on the other page, even though they were still a little bit tricky. Right? But of course, we could have made Maple help us along at different points, but I wanted to do all this work by hand to remind you all of what is possible in a triple integral, if for nothing else. So the actual setup, right, was pretty simple. We had to switch it to polar or cylindrical coordinates, three-dimensional polar. So we switched it to cylindrical coordinates, but other than that, it was pretty straightforward, right? Much more so than the previous way with a surface integral. So that's the advantage of using the divergence theorem. It makes it much easier to work with a closed surface. For one thing, we didn't have to do 2 sets of integrals like we did in the previous method, where we were able to just do one triple integral and it would find everything for us.